Hello everyone and welcome to this webinar for testing analysis principles and practice. I'm 𝐏𝐞𝐭𝐫𝐨𝐦, Reservoir Engineer from Cairo, Egypt. So basically this webinar is designed to introduce an overview of well testing analysis principles, applications, theory of pressure transient, interpretation of well testing and reservoir modeling. So right now let's start directly with our agenda today. Start with the introduction, surface testing equipment, type of pressure testing, basic theory on divisivity equation, and fundamentals of pressure transient. After that, the analysis techniques like type curve matching and the pressure derivative. And then we have reservoir modeling will cover reservoir wellbore models, well models, well testing for hydraulic fractured wells, reservoir models, and finally boundary models. And at the end, we will take an overview about well testing interpretation process. So right now, let's define what does it mean by reservoir engineering and how does it work. Basically, the reservoir engineering is a branch of petroleum engineering which is concerned with the application of fluid flow in the porous media of subsurface reservoirs. So as you can see, assuming we have this cubic unit volume of the subsurface reservoir, as you can see, we have the rock matrix, and in between we have the porous spaces. So the main fundamentals of reservoir engineering, number one is the Darcy equation or flow rate equation to characterize fluid flow in the porous media. The second one is the material balance or continuity equation, because we have a specific subsurface volume or STOIB. Therefore, the remaining volume will be the initial volume minus the produced volume. The third concept is the PVT properties or equation of a state model. As you know, the reservoir flow properties like oil density, oil viscosity, and oil formation volume factor, and so on, are dependent of pressure. Therefore, as we produce from the reservoir, the pressure will decrease from the average reservoir pressure to bottom hole flowing pressure and then to wellhead pressure. Therefore, we have to use a specific PVT model to characterize fluids while this process of production from reservoir to surface and finally to transportation. So for complete system analysis, we can introduce IBR and outflow models for complete system analysis. Right now, what does it mean by well testing? The well testing is simply a pressure or signal is sent into the reservoir. The signal is created by controlled drawdown and shut-in, controlled opens and shut-in at surface. Meanwhile, the pressure response or the pressure transient is recorded by using downhole memory gauges. So as you can see, in this case, we have this signal sent to the reservoir. We record the reservoir response by dividing this response into 3 different periods. The first period is the early time region. As you can see, we have information about the wellbore and the well itself, like the wellbore storage, skin accumulation efficiency of our well. The second period is the middle time region. We have information about the reservoir fluids and the reservoir rock itself, reservoir homogeneity or heterogeneity, more description about the reservoir and identification of reservoir permeability. And finally, we have the late time region. In this region, we have more information about reservoir boundaries, the distance to boundaries, type of boundaries, and the shape of our reservoir. and accordingly we will have information about the hydrocarbon pore volume in our study well. So simply, the well testing or pressure transient analysis is the input signal of a step function of rate. As you can see, the function of rate may be draw down or build up, is sent to the reservoir system. This this input signal is we have output response from the reservoir in terms of pressure response. So in this case, we have to have a mathematical model or the divisivity equation to quantify the pressure response of our reservoir and make the well testing interpretation. So we have input to our model like the flow rates and the pressures and fluid properties, and the model outputs are the reservoir parameters and boundary information. So as you can see, we have important applications and objectives of well testing related to exploration phase. We will able to identify reservoir size, hydrocarbon volumes, productivity of our well. So as you can see, assuming we have this testing well, we have a specific perforation interval and a specific pressure response or pressure profile versus time. And at surface, we have surface measurements in terms of flow rates and pressures. So for the reservoir development phase, we have important information to identify like permeability, connectivity between wells, formation damage, and the characterization of completion efficiency. And within reservoir management also, we have important information we can get from well testing like sweep efficiency, dense drainage, and permeability. So again, we have this downhole murmur gauges to record bottom hole data like pressure, temperature versus time. And at surface, we have a specific surface equipment, surface testing equipment to measure flow rates and pressure versus time. And we have specific equipment for phase separations and metering and so on. And finally, we have to have a specific workstation for data acquisition and analysis and interpretation. As you can see, this is an example of a specific testing schedule. As you can see, we have this sequence for an oil well starting from initial flow after the shut-in. As you can see, the reservoir pressure is constant at the initial reservoir pressure at this level. And we have a specific the first drawdown at this interval. After that, we have initial shut-in to enable to identify the average pressure after short drawdown interval like this. After that, we have flow after flow test like this at different choke sizes or flow rates. The last flow rate or last drawdown is typically extended to reach the stabilized flowing conditions of the reservoir. And finally, we have the final shut-in. This is another field case. As you can see, we have first build-up and several arrangements of drawdown at different flow rates. So for surface testing equipment, or testing facilities, the main objectives of testing or surface equipment in well testing is to control the well while the test and measure surface flow rates and the pressure during your test. As you can see, this is the typical arrangement of surface testing equipment. Starting from the first component in the our system is the Christmas tree. Christmas tree is simply an arrangement of valves and the pressure gauges to control the well during the test. After that, The second important component in surface testing equipment is the choke manifold. The objective of choke manifold is to change the choke size during the well, and also the choke manifold facilitates fluid sampling during your test. The next important component in well testing on the surface is the test separator. It's important for three-phase or two-phase separation and fluid metering. After that, we have atmospheric surge tank to flash any dissolved gas in the liquid and enable the to identify the correct shrinkage factor of oil or meter factor for correct flow rate calculations. Finally, we have the oil may be diverted to the flare or production line or even to storage tanks. This is another simple arrangement. So we have on the subsurface of the downhole, we have downhole moment gauges to record the pressure versus and temperature versus time. We have a specific response from the reservoir, and on surface we have another measurements like flow rate and surface pressures, wellhead upstream and downstream pressure, surface flow rates of oil, water, and gas, and the important three components on surface are Christmas tree, choke manifold, and test separator. To highlight the choke manifold, we will control the well production rate during the test. On test separator, maybe two-phase or three-phase separators based on the type of the reservoir fluid. Surge tanks are important for applying the correct meter factor or a shrinkage factor of the produced oil. And we may have multi-phase metering for more accurate measurements for the flow rates. Type of fuel testing for production well, simply we have two basic types of test: drawdown and build up. Drawdown is simply producing the well, as you can see right here, producing the well at constant flow rate. In the same time, we will record the pressure response. And second type is the build up. Build up is the shutting the well after the period like this, after the period of production at constant flow rate, and measuring the resultant pressure response. For injection wells, we have two similar tests. The first one is the injection uh, test, injecting at constant flow rate and recording the pressure response. The second type is the injection fall-off test, which is equivalent to the build-up in case of production. For gas well testing, we have two typical types of well testing, isochronal and modified isochronal test. Simply, we will make drawdown at 4 different flow rates of equal durations, while the last flow rate in the two types of test will be extended flow period to enable to reach the stabilized flowing conditions. And in between, we have shut-in periods. In the isochronal test, the shut-in period will be dependent of the stabilization of pressure. Therefore, the shut-in period will be long enough to enable the pressure to reach the average reservoir pressure like this. While in the modified isochronal, the shut-in period will equal to the flowing period, whatever we reached the average reservoir pressure or not. The modified isochronal test is commonly used in tight reservoirs because we need to have long shut-in periods to enable the reservoir pressure to reach the initial conditions. Right now, I will highlight the basic theory of well testing, the fundamentals of flow regimes. The flow regimes in well testing simply are the relationships of pressure with time. We have three basic types of flow regimes. The first one is the transient or the unsteady state or infinite acting radial flow. In this case, the pressure will be function of r, which is the radial distance, and t, the time. The second flow regime is the pseudo-steady state or the boundary dominated flow. In this flow regime, the pressure will be a function of R and T as well. But in this case, partial B over partial T will be constant, which means the pressure profile will change throughout the reservoir anywhere in the reservoir at the same rate, so the pressure will decline throughout the entire reservoir at a constant rate. This flow regime is very important to identify the reservoir shape, reservoir area, and finally the hydrocarbon per volume. Second, the third flow regime is the steady state. In this case, partial P over partial T, as you can see, is zero, which means we have no change of pressure with time, which means we have very strong pressure support from aquifer or very effective pressure maintenance operations like water or gas injection. So I'm very simply assuming we have a shut-in well in the center of circular homogeneous reservoir in this situation. So the pressure, as you can see, will be constant throughout the reservoir at the BI or the initial pressure. Once in the this well is produced at constant flow rate, as you can see in this situation. So we will create a pressure disturbance at the sand face. This pressure disturbance will move in the reservoir at a specific rate. This rate or this the velocity of the movement of the pressure transient within the reservoir will be function of K phi mu CT, reservoir mobility, porosity, fluid viscosity, and total compressibility. So as you can see at time t1, the pressure disturbance of the pressure front will reach a radial distance r1. This distance is defined as the radius of investigation. So and at time t2 we have r2 and so on. At time t5 we have r5, which is radius of investigation at this time. So before once because the pressure transient doesn't reach the reservoir boundary, so in this case we have the transient or the infinite acting radial flow, which means mathematically RE or the external drainage radius of our reservoir equals infinity, because the pressure disturbance doesn't see the external reservoir boundary. So we will define this flow regime as transient or infinite acting radial flow. So as a comparison between transient and pseudo-steady state flow, this is the pressure disturbance or pressure transient. Uh, as you can see, at time t1 we have radius r1 and so on. At time t3 we have r3. Well, as long as the pressure disturbance doesn't reach the reservoir boundary, we have the transient or the flow regimes or the pressure transient, as you can see in the green color lines. While once the pressure transient reaches the external boundary of our reservoir, so we have boundary dominated flow or pseudo-steady state flow period. In this case, the pressure profile will decline throughout the entire reservoir at constant rate or at the same rate, like as you can see the pressure profile in the red color lines. So, as the pressure transient timeline, the infinite acting radial flow trend is the fundamental flow regime in all well testing applications. Therefore, the interpretation in starts in 1950s based on the straight line or specialized plots like Horner and DH. In 1970s, we have introduction of log and type curve matching. And in 1983, the introduction is the border derivative, which is the main concept and principle of modern well testing interpretation. And recently in 1990s, we have the introduction of the numerical models in well testing. Simply to define what does mean by the divisivity equation. Divisivity equation is the mathematical model to quantify pressure response and make interpretation of well testing. We have several assumptions in this equation, as you can see. What's important to know the main components or principles of the divisivity equation is the Darcy's law, continuity equation, and equation of state or BVT equation. This is the general form of the divisivity equation for radial flow, as you can see. If we define this term eta as the divisivity constant, so we can define this equation as this form is the generalized divisivity equation for the radial flow. Simply to make a solution for this equation, we have to define initial and boundary conditions. So the initial conditions is the very simple because we have uniform pressure at time zero. In this case, the pressure is constant at Pi or initial pressure. The two boundary conditions. The first condition is we are assuming the well is producing at constant flow rate, and the reservoir will act as it has a infinity or infinite external radius. So we have this generalized divisivity equation. By specifying initial and boundary conditions, we have two different solutions: constant terminal rate and constant terminal pressure. In constant terminal pressure, we assume the pressure at the external boundary if reservoir is constant. In case of strong pressure supports like water influx, while for constant terminal rate, we assume we have constant flow rate during the test, which is the principles of all well testing or pressure transient analysis techniques. We have two different solutions for this scenario: EI exponential integral solution and dimensionless pressure drop solution. For the dimensionless pressure drop solution, as you can see, this is the Darcy equation in the radial flow form. We can easily rearrange this equation in this form. Therefore, we can get any variability, an equivalent dimensionless variable, by just rearrangement of the flow equations like this. By just rearranging, we have this BD dimensionless pressure is a function of dimensionless external drainage radius. The typical pressure response, as you can see, the pressure response will follow this profile. Start from the initial or average reservoir pressure. The pressure will decline till this region around the wellbore. We have typical alternation in the properties of region around the wellbore due to the invasion of drilling fluids and completion fluids and so on. Therefore, we have to define an factor which is skim factor. So the skim factor is important to account any alternations in the region around the wellbore in the EI function solution. So in the we have in the area around the wellbore Ks, which K due to in the skin region around the wellbore, and K, which is the original reservoir permeability, and we have RS, the radius of the altered zone around the wellbore, and RE at the end of external radius. And as you can see, this in the green color, we have this normal pressure profile. In case of we have positive skin damage around the wellbores, therefore we have additional pressure drop in this region, delta BS. While in case if we have an enhancement in the in the permeability around the wellbore, therefore the we will have negative skin, which means the pressure at the wellbore will be higher than expected because we have an enhancement in this region. So as you can see, to account for the alternation in the region around the wellbore, and we have an assumption which states that we have uniform permeability throughout the entire drainage area of the wellbore. Therefore, we have to define delta BS, the pressure drop due to skin, by this equation. So by just rearrangement and replacement, system is defined as a skin factor S, so S can be defined as a function of delta BS. Which is more important right now is to know we have RW apparent, or the effective or apparent wellbore radius. It's an alternative treatment of the skin effect to account for the pressure drop in the area around the wellbore. So RW apparent is a function of the RW and the skin factor itself. Another important factor in well testing interpretation, which is wellbore storage. Typically, wellbore storage is the function to account for in drawdown. For example, we assume the flow rate, as you can see, is coming directly from the sand face, or the flow rate will increase from from zero instantaneously to constant flow rate. However, in reality, the surface flow rate in drawdown will coming from the fluid stored in the wellbore. So in this case, the surface flow rate will increase, will follow this line in the red color, will increase from zero to a constant flow rate. At this point, the EI function solution becomes valid because at this point, the flow rate is directly coming from the sand face and not from the fluid stored in the wellbore. The opposite of this process will be in the during buildup, like this. Wellbore storage is defined by this coefficient C capital in barrels by BSI, which is the change of fluid by change of pressure, change of wellbore volume of the wellbore fluid to the change of pressure in barrels per PSI. So this function, we have the sand face flow rate will equal the surface flow rate plus this term as a function of wellbore storage, as you can see. So if the wellbore storage C capital is zero, in this case, the sand face flow rate will equal the surface flow rate. So we have to use this term to account for the early time of the drawdown or buildup to avoid the distortion of the pressure behavior due to wellbore storage. Right now, we'll highlight the type curve analysis. What does it mean by type curves? Type curve in well testing is a graphical representation of the solutions of the flow equations. Typically, the type curves are represented in dimensionless variables like dimensionless pressure, dimensionless time, and dimensionless radius. Simply, as mentioned before, you can introduce any variable to be dimensionless by just rearrangement. And as you can see, for example, the dimensionless pressure is a function of the pressure itself in PSI times this group of variables A capital. So the units of A capital must be PSI minus 1 to get the units of the BD or the dimensionless pressure as dimensionless or unitless. So, for example, this is the this is equation, but just a simple rearrangement like this. We have this form, so this dimensionless pressure is equal this pressure drop in PSI and this term as of units of PSI minus 1. So this term is the term defined as group A. So group A is the function of K and phi and mu and beta or oil formation volume factor. So by taking the logarithmic of two sides very simply, so the difference between BD or dimensionless pressure and the pressure difference is equal this term or the or group A. Therefore, the vertical shift between dimensionless pressure and the normal pressure is a function of the group A. Simply for and similarly for the dimensionless time, as you can see, it's equal the time itself in hours times this group B. In this case, the units of group B is 1 over hour or hour minus 1. Similarly, the horizontal shift between TD and the time itself will equal the group B. Simply, if we make type curving and if we override the plots of dimensionless pressure versus dimensionless time, and we override in the same plot the pressure difference versus time. So we have two curves. If the two curves are matched together, so it's the process of type curve matching. As you can see, the vertical shift is the difference between BD and delta B is a function of group A, which is this variable, and the horizontal shift between the TD dimensionless pressure and the dimensionless time and the time itself is this variable, which is group B. So if the two curves are matched together, in this case, the reservoir parameters will be the data of the type curve. This is simply the process of type curve matching, and this is the principle and the concept of well testing interpretation. So the first type curves are the graying out type curves. As you can see, these type curves are typically functions of the three components: the dimensionless pressure in y-axis and dimensionless ratio in x-axis, and the value of the type curve itself is a function of dimensionless characterization group like this. So, but we have a clear problem with the Green-Garten type curves because the curves are very similar to, and in this case, we have high uncertainty to identify the correct type curves that match our reservoir data because the all type curves has similar shape without any clear difference between them. Therefore, in 1983, Bordat introduced the concept of the pressure derivative. The pressure derivative, as mentioned, is the slope of the semilog plot plotted in the log-log coordinates and combined with the delta B or the pressure difference curve. This is the definition of the pressure derivative, T delta B over delta T. So in this case, the pressure derivative is highly important because And the green garden type curves, they are very similar to each other without clear changes between them. But in case we have the pressure derivative, so you will match your data on two different curves. The first curve is the pressure difference, which is this, and the second curve is the pressure derivative. So this is the type curve. As you can see, we have this curve is the pressure difference, and this one is the pressure derivative. Uh, at first and during the Wellbore storage effect, we have this definition of Wellbore storage of delta B as a function of the variable C capital. So by taking the pressure derivative, T delta B over delta T will equal, as you can see, will equal delta B. Therefore, the pressure difference and the pressure derivative will have a unit slope straight line on the log-log plot during the Wellbore storage effect. So as you can see, once we have a unit slope straight line on the log-log plot of the pressure difference and the pressure derivative, so we have a Wellbore storage effect. Once we have a deviation from this unit slope straight line, so it's the end of Wellbore storage effect. For the infinite acting radial flow, we have this equation to characterize to define the pressure difference. To define the pressure derivative, as you can see, we will have this will equal this variable. So the pressure derivative, as you can see, during the infinite acting radial flow or the transient flow will be a horizontal straight line or a straight line with zero slope. As you can see, this line of this stabilization line of the pressure derivative will be function of these variables. Mainly, it's a function of the reservoir permeability. If we assume we have a constant flow rate, constant fluid properties like oil formation volume factor, oil viscosity, and we have constant net bay interval H. Therefore, the stabilization level of the pressure derivative during the infinite acting radial flow will be a function of reservoir permeability. So simply, well testing interpretation is to match your field data on the type curve of the pressure difference and the pressure derivative. We have at first we have Wellbore storage effect at the early time. In this period, we have unit slope straight line in both pressure difference and the pressure derivative. And in this transition, we have the effect of the skin damage, and finally, after that, we have the reservoir effect, which means we have this horizontal derivative, which means we have infinite acting radial flow. The this stabilization level of derivative is a function, mainly a function of reservoir permeability. And after that, we will have the effect of reservoir boundary based on the distance and the type of boundary. So as you can see, this our field data is plotted in this type curve. We will change the parameters of the type curve and try to match our field data. In this case, once the data is matched, we will have the reservoir parameters related to reservoir boundaries, reservoir description, and also the wellbore and well parameters like completion efficiency, the value of skin, and the value of wellbore storage. So to highlight reservoir modeling and interpretation process in well testing, we have to identify early time region and get the values of wellbore storage, value of skin, and other parameters like the fracture characteristics in case we have hydraulic fracturing. For middle time region, we have to identify reservoir characteristics based on the type of reservoir, maybe homogeneous or heterogeneous reservoir. And finally, for the late time region, we have to know the reservoir boundaries and the type of boundary, no flow boundary or constant pressure boundary based on the pressure support at boundary. So for the Wellbore models, we have the first model is the constant Wellbore storage, which means we have the Wellbore storage is constant during the test. Wellbore storage, as defined before, is C capital, and this equation will be used to define Wellbore storage. Wellbore storage, as mentioned, during Wellbore storage effect, we will have a unit slope straight line on both curves of the pressure difference on this group of curves and the pressure derivative. As you can see, if we have very low Wellbore storage, like this curve in the green color, so the end of Wellbore storage will be at early time at this point, and the start of the infinite acting radial flow will coming early as well. While in case we have high Wellbore storage like this one in the purple color, Wellbore storage is zero point 0.1 barons per psi. So the end of Wellbore storage at this point will coming late, and also the effect of Wellbore storage will delay the time of the infinite acting radial flow or the horizontal derivative at this point, as you can see. So, similarly, to highlight this point, the Wellbore storage, if we have significant Wellbore storage, so it will mask the other characteristics and other features in your test, like the fracture linear flow or reservoir features like dual pose, the radial first fracture radial flow. So the second type of wellbore storage is changing wellbore storage when we have increasing or decreasing wellbore storage based on the compressibility of the fluids in the wellbore during the test. So in this case, we have drawdown and increasing in wellbore storage. So we have this straight line and we have shift on this line to the right, which means we have increasing in the wellbore storage. While in this case, for the build-up, we have decreasing wellbore storage. So at this point, as you can see, we have this unit slope line. After that, we have a decreasing in the slope or shifting in the slope of this line, which means the end of wellbore storage becomes early, which means we have a decreasing in wellbore storage. For the well models, we have, as you can see, we have different well models like the vertical wells, partially penetrating wells like this case. We have partial perforation across the zone interval. We may have limited entry also like this, spherical or hemispherical flow. We may have horizontal wells or even fractured wells. A skin effect, as mentioned, the skin is an additional pressure drop due to alternation in the region around the wellbore. In case we have damage, we will have positive skin, uh, typically due to invasions of drilling fluids and completion fluids, or maybe the efficiency of completion itself. So the effect of a skin, as you can see, a skin will typically change the amplitude of the hump of the pressure derivative. So as you can see, this green line, we have a skin is -3. So the amplitude of the hump on the pressure derivative is very low, maybe 0. While in case of this model, in the purple color, the skin is very high. We have positive skin, +10. So the amplitude of this hump is large. Also, skin will affect the semilog plot. So if we have low skin, so the deviation from the semilog straight line will be very low. While in this test, in this model, we have a very high deviation from the semilog straight line. Also, for the history plot, if we have high skin, as you can see, we will have a very high pressure drop during this interval, or this drawdown interval. While for negative skin, the pressure drop is very low during the drawdown. To highlight hydraulic fracture dwells very quickly. The objective of hydraulic fractures to mainly to bypass new wellbore damage and extend new conductive flow passes to improve the reservoir productivity. So similarly, we have these hydraulic fractures parameters. The most important one is the XF, or the fracture half length. This is the wellbore, and this is the shape of our fracture. In well testing interpretation, we have two basic fracture models. The first one is the high or infinite conductivity fracture. In this case, the pressure drop along the fracture is neglected. And the second one is the low or finite conductivity fracture, which means we have significant pressure drop uh, along the fracture. Simply to highlight different flow regimes for the fracture dwells, as you can see, the first one is a fracture linear flow. The flow is linear across the fracture, and the pressure transient doesn't reach the end of fracture. Second one is the fracture bilinear flow. In this case, we have the flow along the fracture and perpendicular flow from the formation near the fracture. And then the formation linear flow, we have a flow from formation to the fracture itself. And finally, we have pseudo-radial flow, or formation radial flow. In this case, we have radial flow from the formation to the fracture itself. So we have two examples of the fracture as well. As you can see, for the fracture linear flow, we have this model. In this case, the pressure difference, this one, and the pressure derivative will have half a slope straight line, as you can see, because as defined right here, the pressure derivative will be a function of half times this variable, or this product. So this is the typical behavior of the fracture linear flow on the log-log plot. While the fracture bilinear flow, as you can see, the pressure difference and the pressure derivative will have half a slope, 1/4 slope straight line, because the pressure derivative in this case, we have this parameter 1/4 the times this variable. For the reservoir models, simply we have two types of reservoir models. We may have homogeneous reservoir or single system, and heterogeneous reservoir like dual porosity, like this model, dual permeability to like to region to intervals reservoir, composite systems or radial composites and so on. So to identify different types of reservoir models, the homogeneous reservoir, as you can see, we have only mobility, only one mobility KH over mu like this, and one storativity of phi mu CT, or the reservoir is homogeneous because we have single system, single reservoir permeability, no changes in reservoir permeability throughout the reservoir. The second type is dual porosity system. In this case, as you can see, we have two components of the reservoir. So the first component is the matrix blocks, and the second component is the fractures. So in this case, the flow will be from the matrix blocks to the fractures, and from the fractures to the well. The dual mobility system, as you can see, we also have two components, like two layers of different mobilities, K1 and K2. So when we have flow from K2 or layer 2 to layer 1, and flow from layer 1 to the wellbore, and maybe from layer to the wellbore itself. And also we may, in this case, we may have a cross flow between the two layers based on the pressure difference between them. For the composite system, as you can see, also we have two components. So in this case, the reservoir is divided into two regions of different mobilities and storativities. So for homogeneous reservoir, as mentioned, the reservoir, it's the simplest reservoir model. We assume we have same porosity, permeability, and thickness throughout the reservoir. The permeability is isotropic, which means the permeability is the same in all directions. So as you can see, this is a shape of the log plot. We have pressure difference and the pressure derivative. We must have a stabilization in the pressure derivative. As you can see, this the down movement on this derivative means we have increasing in reservoir permeability. Also, the effect of the skin will affect the amplitude of the hump on the pressure derivative. So if we have high skin, we will have a large hump like this model. So this is the effect of skin will affect the hump on the pressure derivative, and this is the effect of permeability. So higher permeability will move the pressure derivative, as you can see, down. So you will have the stabilization level lower, like this model. For the dual porosity models, as you can see, the reservoir have two components. The first one is the matrix blocks with high storativity and low permeability. The and natural fractures, typically have low storativity and high permeability or high transmissibility. So, and to understand the pressure response in this model, the flow will be from the matrix blocks to the fractures like this, and the fractures to the well, which means we have no direct flow from matrix blocks to the well. So the controlling parameter in this model, the parameter omega, which is the storativity ratio, and lambda, which is the interporosity flow coefficient. So the pressure behavior in the dual porosity models At first, once we have the pressure drop in the bottom hole flowing pressure, so the fractions like this will start to flow to the wellbore. So at first we have the first fissure flow, the infinite acting radial flow of the fracture system, or initial fissure flow or initial fracture flow. After that, once we have a pressure drop between the matrix blocks in like this and the fractures, so the fractures will start to flow the matrix block will start to flow to the fractures. So in this case, we will have this transitional dip. So this dip, which means we have flow, the start of the flow from matrix to fractures. After that, for the total system, we have fractures plus matrix flow. So as you can see, the pressure derivative will stabilize at the same level, which means we have total system flow or total system infinite acting radial flow, highlighted by the horizontal derivative at the level of the fracture flow. So simply we have the first infinite acting radial flow for the fracture, and in between we have transitional dip, and finally infinite acting radial flow for the total system. So this is an example of dual porosity system. At first we have this for the Wellbore Storage unit slope straight line and this hump for skin, and first the first radial flow for the fracture, and then the transitional dip, and finally the radial flow for the total system. Composite systems very similar. As you can see, we have the system will have two components or two regions of different mobilities and storativity. In this case, we have inner region around the wellbore region number one, and the outer region away from the wellbore. We may have changes in the fluid or the rock property between region one and region two. The controlling boundary in this model are M mobility ratio and D, which is the divisivity ratio defined by these equations. And in between we have this interface or the radial or the linear or radial distance. The assumption is the no pressure drop across the interface between the inner and the outer region. So the radial composite response, as you can see, we have two stabilization levels. At first, we have a straight line for Wellbore Storage. After that, we have this hump for skin to dependent of skin value. After that, we have the radial flow for the inner region and another stabilization level for the outer region. So the second stabilization level, as you can see, will be dependent of the properties of the outer region or the mobility and storativity of the outer region. So and simply the down movement in the pressure derivative means we have improved in the flow mechanics, increase in KH and increase in mobility. This is a field example of the composite models. As you can see, we have this injection period at injection rate about 10,000 barrels per day, and followed by this follow-off period for this period highlighted in red. This is the shape of log plot. As you can see, we have the unit slope straight line for Wellbore Storage, and then this hump for skin. After that, we have first stabilization level for the inner region and second stabilization level for the outer region, which means we have changes in fluid viscosity, which is very applicable in case of injecting water in an oil reservoir. This is the final matching of this model. Finally, we have to highlight the boundary models. Boundary models in well testing, as you can see, we have different types of boundaries. Maybe single sealing fault at distance L, two parallel faults and two at distance N and S, north and south distance, two intersecting faults like this, and we have angle theta between them, closed system like circle or rectangle. Simply to highlight the boundary effects, we have the pressure transient will pass through three periods, as you can see. The first, assuming we have this reservoir boundary, and this profile in the red color is the pressure transient or the pressure profile. So at the first period, the the pressure transient doesn't reach the reservoir boundary. For the second case, the pressure transient has reached the reservoir boundary, but not reflected at the wellbore. After that, in case number three, the pressure transient has reached the reservoir boundary and also reflected at the wellbore. So in case we have closed system or pressure support, so the pressure profile will be stable or stabilized at initial reservoir pressure. If we have depletion or no flow boundary, so the reservoir pressure will decline with time like this. To simulate the boundary effect of well testing, we use the concept of images. So we can simulate the effect of single reservoir boundaries, sealing boundary, for example, by assuming we have an image well at equal distance of our well. This will introduce an additional infinite acting radial flow to the tested well, which means we have additional pressure drop due to the boundary. So this is the effect of the pressure transient during the infinite acting radial flow, and this behavior during the constant pressure boundary. So we have pressure support from the boundary like water aquifer or water injection operations. So the boundary is highlighted by introducing, for example, we have additional radial flow from the boundary, which means we have additional pressure drop due to an image well at equal distance from the boundary. Similarly, if we have single sealing fault, as you can see, this is the tested well, and this is the sealing boundary. So this scenario, this model is simulated by assuming we have a virtual or image well at equal distance L from the boundary. So the solution will be defined by superimposing the two infinite acting responses. So as you can see, this is the typical log-log plot for a single sealing fault. At first, we have unit slope straight line for wellbore storage and this hump for skin. After that, we have a stabilization in derivative due to the infinite acting radial flow. And at this point, we have the boundary effect or the start of deviation in the pressure derivative. In case we have sealing faults, so as you can see, the pressure derivative will stabilize, will deviate upward and stabilize at twice stabilization level, while for constant pressure boundaries, the pressure derivative will go to zero, which means as you can see, the pressure is stabilized, while for a no flow boundary, the pressure will start to decline. This is an example for single sealing fault. As you can see, the distance to the fault is the distance L, is the major parameter in this model. So at a lower distance like this model, so the boundary effect will coming early, while for the far distance like this model, the boundary effect will coming late, like this case. For two intersecting faults, it's very similar to single fault. We have two intersecting faults, and we have angle theta between them. So at first we have this level stabilization due to radial flow and deviation in the derivative at this point. So as expected, we once we the pressure transient, once the first fault is detected, we will have a deviation in the pressure derivative, and after the second fault is detected, we will have additional, at this point, as you can see, additional deviation in the pressure derivative. And as you can see, the final stabilization level in this model will be dependent of the angle theta between the two faults. This is an example of the two intersecting faults. As you can see, we have this sequence. This is the history plot. This is the fluid versus time. This is the recorded bottom hole pressure versus time. And by constructing the log plot, as you can see, we have this stabilization which reflect the radial flow or infinite acting radial flow. We have first deviation in the derivative at this line, as you can see at this point, which means we have effect of the first fault, while at this point we have a second deviation in the derivative, which means we have additional fault. The interpretation and matching of this model is using two intersecting fault. This is the final matching of this model. So for the boundary, we have two intersecting faults, and this is the distance between from the well to the fault number one, L1, and the second fault, the distance L2, and the angle theta between the two faults is 92 degrees. For circular boundaries or closed system, as you can see, we assume the reservoir is the center of circular homogeneous reservoir of external radius RE. So the behavior of the log plot in this case will be dependent of the type of test, drawdown or build-up, and the shape of the boundary, circle or rectangle. So this is the typical response for the closed circular reservoirs. As you can see, at first we have Wellbore Storage, followed by skin, infinite acting radial flow for the horizontal derivative, and deviation for the drawdown. As you can see, if we analyze drawdown interval, so the deviation at this point, the pressure derivative will have a unit slope straight line, which means we have pseudo steady state flow, while during the build-up period, as you can see, the pressure derivative will go down, which means we have a closed system. So the circular closed system is defined by unit slope straight line during the drawdown interval on the log plot, and the down movement on the derivative to 0 during the build-up periods. So closed systems may be circle or rectangle. During drawdown, we have unit slope straight line uh, because we have pseudo steady state flow, while for build-up, we have the pressure derivative will go down like this because and the pressure difference, as you can see, will be stabilized at the average reservoir pressure. This is an example of the boundary effect in closed systems. As you can see, we have this schedule of drawdown and build-ups. At first, analysis number one is the build-up analysis. We will analyze this build-up interval. As you can see, this is the shape of log plot. We have Wellbore storage, a skin followed infinite acting radial flow, and then the boundary go down, which means we may have constant pressure or closed system. To confirm our results, we will analyze this drawdown interval analysis number two. As you can see, the pressure derivative in this case has a unit slope straight line, which means we have a constant a closed system. So in this case, we have confirmed the results using drawdown and build-up. So to summarize all boundary models, as you can see, at first we have the first stabilization or the infinite acting radial flow at stabilization level M. At this point, we have deviation in the pressure derivative. This is the responses of the pressure derivative. If we have on the slope straight line during the drawdown, so as you can see, we have a closed system. In case we have this response, the derivative is stabilized at twice a stabilization level, means it means we have single sealing fault. At 4 times the stabilization level of the infinite acting radial flow, we have two intersecting faults. The angle between them is 90 degrees. For two intersecting faults of angle theta, so the stabilization level will be 360 degrees over theta times m, where m is the level of infinite acting radial flow. For the two parallel faults, we will have half slope straight lines at pressure derivative. Also, for the closed system on the build-up, we will have this response. Also, for single sealing fault with constant pressure, also the pressure derivative will go down as mentioned. And also for the two intersecting faults like this, in case of a constant pressure boundary, the pressure derivative will go down to zero like this model. So finally, to summarize well testing interpretation, we have recorded data. We need to identify the reservoir model by interpretation and matching of our recorded data using type curves. We need to identify the early time parameters related to well bore and well characteristics. For the middle time related to a reservoir itself, and lead time, which means the parameters or data related to the boundary. After that, we have to calculate model behavior and compare with data and check consistency of your model with the geological parameter and fine tune to get the final interpretation. Finally, in this webinar, I'd like to highlight some important rules in well testing. Any sudden effect in well testing is not related to the reservoir. The longer flow period, which means we have more information uh, or more data or about the reservoir. The In well testing interpretation, you have to match the end points, the or anchor points, the start and end of every drawdown and build up interval. The wellbore transients may mask the reservoir transient. The software or the computer is only a calculator. In this case, you have to get consistent match because you are the interpreter. And finally, start well testing using simple models and add more details step by step. So that's all I have in this webinar. Thank you so much for joining me. And right now, feel free to ask any questions.